Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're going to get started. I want to thank everyone for coming today to our workshop on quantum algorithms and devices. We have a really exciting day lined up. I have to say I'm really excited to see so many new faces in the audience. We did not expect such a crowd, so looks like you have to get to know your neighbors today. We had a quantum session at the Faculty Summit for the first time last year, and it was really popular and a hit. So we had a second session this year. So this is the second time we've had a workshop in conjunction with the Faculty Summit. And I have to say this year it looks like we have about double the crowd. So this is really exciting, and I hope it kind of shows how much more popular quantum computing is becoming here at Microsoft and also in the academic community. So thank you everyone for coming. We had a great quantum session yesterday with talks from Rob Scholkoff, David Riley, and Dave Wecker. Today in the middle session, Rob and David are going to give us a more technical, detailed talk on the hardware devices and the control engineering required. So that'll be great. This morning we have a series of talks where we're going to learn about what you can do when you have an untrusted quantum computer. So that should be exciting. Then this afternoon we'll hear a little bit more about some work in quantum algorithms, what we can learn about space-time from quantum information, also new applications to materials, how we can use quantum algorithms to explore material science, and so on. So it should be a really exciting day. Thank you again, everyone, for coming. And I think we'll just get started. So the first talk we have this morning is from Yaoyun Shi. And Yaoyun is going to talk about true randomness, its genesis and expansion. So let's welcome Yaoyun.
Thank you. Thank you, Krysta, and thank you all of you to be here. And it's really an honor to be here. And I've been a theorist all my professional career. And that I'm in a company talking about my work make me feel that my work actually is relevant to reality. So that's so thank you very much. So randomness means different things to different people. So I will start by describing what I mean by randomness and why is it difficult to get randomness, and why we should consider quantum approach for generating random numbers, and in particular, using untrusted quantum devices. So what's randomness? Suppose we have a n-bit string x, and I call it random with respect to a quantum system E, if the string x cannot be perfectly predicted from the system E. So randomness is relative. What time I had breakfast this morning, I know it, but it's random to you. So uniform randomness means that the string x is uniformly distributed, and it is in tensor product with the system E. So there's no correlation between x and E. Nk source means that the string x has n bits, but for the system E, the best chance of E predicting x is no more than 2 to the minus k. So if n is precisely k, the only possibility is this uniform randomness. There's no correlation between them. And when k is strictly less than n, we call x a weak randomness, a weak source of randomness. So we will be talking about errors. So by error, I mean a deviation of the joint state x and E from this uniform distribution case. Deviation could be trace distance. And I will be talking about true randomness. What I mean is when parameters of my protocols grow, when I use more resources, then this error will go to 0. That's what I mean by true randomness. Okay, those are my terminologies. So we need randomness. We need them a lot. Randomness is critical for cryptography, privacy, and is vital for running randomized algorithms, for simulating physics, for gambling. And I think we need so much, probably 1 terabyte a day in the whole world. It's not a exaggeration. I saw Burden laughing. I'm not sure. Do you think that's reasonable? Or if
Small.
maybe this is too small. Okay. At least low bound. This is low bound. Actually, in fact, most of randomness we use, they don't come from the keys. The keys are only a small portion of it, at least according to my security colleagues. So every internet packet has a header, which is supposed to be a random number. So the central question is, how do we get true randomness and know that we are getting it? The reality is that we are not always getting true randomness. And there are many security problems in the practical systems we are using. I wanted to quote a research done by my colleague, Alex Haldeman, and his collaborators, Hellinger. So they downloaded a lot of keys, DSA keys and RSA keys from internet. They didn't try to factor every one of the public keys, but they tried to look for pairwise shared factors. And they ended up breaking 1% or 1.5% of keys. And the reason is because there are so many key sharing factors with each other. We know GCD is easy to do, right? And there are a small number of device makers, probably 80% are in Taiwan, and producing those hardwares, and they all use similar methods to get an initial randomness. So there just isn't enough entropy to start with. So there are other problems. We know from newspapers that there are hardware and software backdoors for random number generators. So Hellinger and co-authors, they stated in their paper, secure random number generation continues to be unsolved problem in important areas of practice. Yes, Matt.
So what you said, did they simply take a large number of pairs of keys and just run GCD and
they didn't run the naive pairwise GCD, but essentially that's what I did. They run a more clever algorithm. They will find out if there's any pair that share a factor. They will find out that share a factor. Yeah, it's a clever way of pairwise GCD.
They suspected that the hardware implementations didn't have enough entropy, and that was true.
So the primes are supposed to be random, but they are not sampled randomly. That's basically the theoretical reason why there are so many shared factors. So it's a difficult problem. So why is it a difficult problem? So here's a cartoon, Dear Bird cartoon. So this random number oracle is giving out its random numbers, and which is a sequence of 9. It doesn't seem random to us, but it's the same probability of occurring with any other sequence. There's just no way to test if an output is uniformly distributed for a simple reason, because uniform distribution is a convex combination of deterministic distribution, if I can call it that way. So there's no way to differentiate these two cases. And it's also a deep mathematical and physics question. It's not clear at all that randomness exists in the whole world. It's all possible that we all this may look terrible to some people. I apologize for that. But I'm a fan of the movie, so you probably know which movie I'm referring to. So it's possible that we are all sitting in this environment that we feel that things are random, but some higher being knows what's going on, right? And we just can't possibly know. And it's possible that quantum mechanics is a correct theory of predicting our observation. At the same time, everything is deterministic. There might be some magic book having every setup of experiment recorded, and then the outcome of the experiment also recorded already deterministically. And we are just reading off that deterministic book. It's possible.
Are we reading it randomly? Are we reading it randomly?
No, we are reading deterministically. And yeah, it's random to us, but for this higher being, it's deterministic. It took me a while to feel comfortable accepting quantum mechanics correct at the same time. The work could be deterministic.
How does your definition of randomness compare with, say, Kolmogorov complexity or other definitions of randomness?
Yeah, I think it's very different. Kolmogorov uses this program size to describe randomness, right? The size of the smallest size of a program to generate a sequence.
You didn't define what a guess was.
Sure, I can define it. So imagine you have some classical string, right? Some secret X, and I'm the rest of the universe, okay? And I'm trying to predict your secret. So what I can do is to apply whatever local measurement on my system and come up with a number. And that's my guess.
Do I have to write down X before you try to guess it?
No, I don't know what you are. So I know you have some string. And suppose I know the length of a string. And I'm trying to come up with a guess. So you have X. I'm going to come up with X prime. X prime comes from the measurement outcome that I get by measuring my own system. So I can choose the best measurement, I think.
So all your strings are finite. You're not deleting
All my strings, I have quantum system. I have quantum sign information about your secret. You can even assume this is an infinite dimension. I think it works. Our proof should work for that as well. So for our question to make sense, we have to assume there's weak randomness in the world. Now, assuming that the world is not deterministic, there's some weak randomness. So now the question becomes, could there be almost perfect randomness, assuming we have weak randomness to start with? So a negative answer to that question would be, maybe we are stuck with weak randomness. There's no way for us to amplify randomness to almost perfect randomness. So it's a deep physics question. So let's look at how people, what are the tools developed in the past for getting true randomness. So there's a theory of randomness extractors developed in the 80s. Started in the 80s, and now it's still a very active research area. So in this theory, weak sources, they are modeled by mean entropy. So we describe the length and the mean entropy. And the extractor is a deterministic procedure. So it takes weak sources and output some string so that under some assumptions, about those weak sources, the extractor is so cleverly constructed so that the output is guaranteed to be true randomness. So that's a classical theory. And when one of the sources is uniform but very short, there's a very short seed you start with, they are amazing constructions, non-trivial constructions that guarantee very good performance, almost optimal performance in the output. But there's a limitation to that theory. One major limitation is it requires two independent sources to start with. So in particular, if there's only one single source, in which case we call it deterministic extraction, then it's impossible even just to get one bit. And this was done by Sensa Vasarani in the 80s. And this is Umesh Vasarani. So we require two independent sources. And of course, if one of them is uniform, that is independent of the other. But there are also constructions that neither has to be uniform, but they do need to be independent. If they are only slightly correlated, we can't even extract one bit. It's impossible to check if two sources of randomness are independent. For the same reason I pointed out earlier. So you have independent distributions, but a convex combination of them could be highly correlated. So there's no way just to tell these two situations apart. And there's probably strong correlation between these two sources. Okay, then so this fundamental limit is one reason that we should consider quantum approach. And of course, there are more reasons to do that. The most important reason is, so quantum mechanics in its postulates has perfect randomness in it. So if we prepare a quantum state in the plus state and just measure using computational basis, we get a perfect coin outcome. And in fact, commercial products are available. And I want to point out that trusting the quantum device, so I'm talking about trusted device random number generation now. And if we trust the quantum device, it's actually a very strong assumption. It implies an independent source. Because if you trust the device, you trust the state is the plus state, and you trust the measurement is doing computational measurement, then you get perfect coin. You get, in particular, you can get independent bits out. So it's a stronger assumption than independence. So this is a commercial product. I hope this slide will not annoy anybody in the audience. So this is taken from from the website of ID Quantique. Okay. I didn't doctor it. Okay. It claims, so this is a product of the company for generating random numbers using quantum technology. I don't know what's inside. I heard it's based on photonics. I'm not sure it's right or not.
We opened it and it's not what you think it does.
Okay.
You have to look at the pattern number. And when you look at the pattern, then you know what's really inside and not look at the web page.
I see. So now I'm convinced that I'm not going to annoy anybody after you speak up. Yeah. Okay. Thank you for that information. Right.
And we don't know what is quantum.
Okay. Good. Yeah, that's interesting. Okay, so I didn't open it up. I didn't look at the pattern. I looked at what they said. Okay. They said that their device passes all randomness tests, which I know is mathematically impossible. And they also say it's officially certified by some 5-letter agency, maybe of a Switzerland government.
To ask them what that means, that it's officially certified.
Yeah, I don't know what it means.
It means they've been asked to run one test suite.
Okay.
And they certified that running that one test suite, the answer is it passing that one test suite.
I see. Thank you for that information. Thank you.
It doesn't mean that it's random.
Okay.
It just means they certify that it passes that one test.
Sure. Okay, good. Actually, right, so I heard that they sell a lot to casino companies. And that's precisely those casino companies need, that there's credibility. So, exactly.
Not the quantumness.
Exactly. Or the randomness. Yeah.
So I have another question. How do you know this state is precisely 1 times ket 0 plus 1 times ket 1? I mean, you're asserting that it's on the equator of the Bloch sphere with perfect accuracy. There's been no change whatsoever. The coin is absolutely fair.
It doesn't have to be.
That seems outrageous.
That's not needed.
I know, but I mean, the claim that it's a perfect generator and passes all tests, well, if I get 1% more ones than zeros when I measure it, that's a test that will fail if it's not absolutely fair.
But you can always apply von Neumann's trick.
You can apply tricks. The assertion was the thing is passes all tests. There's a test. Does it pass that no matter what? I doubt it.
Yeah. Okay.
It did not
So,
pass our tests.
Okay, so I'm going to bring out some similar doubts. Okay, so how do we know it works? Right, it's the same question you're asking actually. So we are not quantum beings, we're classical beings. We can't put our fingers into that device and say, wow, this is beautiful, showing us cat state. We can't do that. And there's another question, are we willing to trust the manufacturer or the certifying agency? I guess after the comment, we probably would not. So even if yes, we trust them, the devices themselves might not be reliable after some time. Right, so we're still facing the question of how do we know this thing is working according to its specifications. So those considerations motivated untrusted device quantum cryptography. So in this model, we interact with those devices through classical interfaces. And the devices themselves might be entangled with themselves and might even have been prepared by the adversary. Okay, that's the worst case scenario that we're going to deal with. So there's no assumption about inner working, and device can be imperfect or even malicious. So the question is, can we still reap the quantum benefits by using those untrusted quantum devices? And the answer is yes, we can. We have to work with them, and we can still make use of them. So this area of untrusted device quantum cryptography started with the question of quantum key distribution. And now it has a few directions. I think Ben is going to talk about a parallel closely related direction of untrusted quantum computation in a sense. So our task is to create and expand true randomness using untrusted quantum devices. So that's our goal. So I'm going to talk about what has been done and introduce our model and state our results. So there are two lines of research before our work. One is called randomness expansion, studied by QuaRC in his thesis. A later paper appeared a few years later with some new content. So here's the setting. So we have some untrusted devices, and we start with some small number of bits that are perfectly random. And making use of those devices with the help of the perfect seed, at the end we hope to output a large number of output bits. So there have been security proofs against the classical adversary and in restricted quantum, against the restricted quantum adversaries. And the first quantum security was proved by Vazirani and Vidic in 2012. And so another amazing property that Vazirani and Vidic proved is that the growth of the length is exponential. We start with k bits, we get exponential in k bits out. So they have these two amazing results. So the second line of research is called randomness amplification, started by QuaRC and Renner more recently. So they were motivated by the question. So those two were physicists, they asked the question, are there fundamental randomness in nature? So we need to model what is weak randomness in nature. So here's their model. You have a sequence of events. Each one is a binary bits. So each one is a bit. And for every bit I, the bit has certain randomness conditioned on previous bits and the environment. Just think about what it is. So the chance of it being 1 is between half minus epsilon and half plus epsilon. So epsilon is a parameter describing the weak randomness of the world. So starting with this weak randomness and making use untrusted quantum devices, they were able to output 1 bit of arbitrarily high randomness, meaning arbitrarily close to 1/2. When the length of the strings grow, then the closer that 1 bit will be to perfect randomness. So a later paper by Gallagher and co-authors show that this is true for any epsilon less than half. So previous paper shows that when epsilon is small enough, you can amplify the freeness of the free will. And later papers show that as long as epsilon is bounded above by 1/2, then you can extract 1 bit. And a more recent paper reduced the total number of devices to be a constant. So those works all assume certain independence of the source and the devices. Still some independence assumption there. So those were 2 lines of research before our work. So I'm going to present a unifying framework, and we call it physical extractors. So in this framework, there are 4 entities. The first one, the particle, it's deterministic. And there's this adversary, which is quantum and all-powerful. And the adversary may be entangled with the devices, and he might have been the person making those devices. But we have a restriction that once the protocol starts, there's no interaction between the adversary and the devices. We have to isolate those devices from the adversary. And this is an assumption that we also have in the classical cryptography. If you're doing something secretly, you have to require that the components you are running your algorithm on, they are not sending out signals to adversary. All right, the third entity is the collection of devices. They are not interacting among themselves once the protocol starts. And in principle, we could put them far apart and relying on spatial relativity to enforce no communication. But in practice, it may be difficult. Okay, the fourth actor in this game is this min-entropy source. So this is a classical bit string that has certain unpredictability to the adversary and the devices. So the min entropy of the source is with respect to the joint system of the adversary and the devices. So that's the setup of our model. So what are the goals? Actually, let's look at expansion and amplification as physical extractors. So expansion is simply seated extraction, meaning that the input x is a uniform string and not created with the device or adversary. And amplification is a 1-bit extractor with some strong assumption about the source. And I'm going to jump to what are the goals of this model of physical extractors? We want to accomplish a few goals. We hope to have quantum security. The output should be random with respect to the all-powerful quantum adversary, as opposed to computational security. So we are looking at information theoretical security. And we hope to minimize error. There are two types of errors, and the error of rejecting honest implementation and the error of accepting bad outcome, or being fooled by malicious adversary. So 2 types of errors we want to minimize. And we hope to maximize the upper length, and we want to minimize the requirement on the classical source. We hope to work with the broadest possible classical source. And we hope to tolerate a constant level of noise of the devices. We are still not capable of doing everything perfect in quantum, so we hope to tolerate that. And we also want to do things efficiently, reducing the requirement on quantum memory, the number of devices that we need to separate, we need to restrict communication of, and the running time should be short. So those are the goals. So now we have this model, and our goal becomes constructing physical extractors with optimal parameters. So let me state our results. The first set of results, this is done with Carl Miller. So this is for seeded extraction. So we start with a small sequence of uniform bits. Let's call it K. Suppose we have K bits. And we have two devices that we can restrict the communication between them. In the end, we produce exponential in K bits, and it's close to uniform random to the all-powerful quantum adversary, so it's quantum security. So those aspects match the result of Wazian analytic. So what are the new results? So the error in our protocol is negligible in the running time. So we achieve cryptographic security for the first time. So previous security is only inverse polynomial. So the error, so remember n is going to be the running time. So this is a function that grows slower than any inverse polynomial. So t could be arbitrarily large constant, could be 100 million. So there is a trade-off between this constant t and this exponent in the output length. But any t and s whose product is less than, say, 1/2 is unadmissible. So our protocol is also robust. If the devices are some small enough universal, some small enough constant below optimal, everything still works.
There would be C in there, right? T times C plus T times S.
That's right. Thank you. I'm sorry, it's a typo. Yeah. So the quantum memory needs only to be 1 qubit for each device component. And so the two devices, they play a London game, they consume that entanglement, but then they can communicate to establish new entanglement, and then in the next cycle, play the next game. So they only need to hold 1 quantum bit each component. And there are many building blocks that works in our protocol, and the proof is just completely different. Okay, that's the first set of results. The second set is done with Chung and Wu. So this is for seedless extraction. In other words, now we don't have uniform randomness to start with. We have some NK source, just one bit entropy source, which we know classically is impossible to extract even 1 bit. So now we have one source, and in fact, our protocol works even if the source is completely known to the adversary. So the mean entropy K is with respect to the devices. Remember, we have a restriction of no communication between them. That's why even if the adversary knows completely the input, he can help the devices during protocol. And so this mean entropy K can be arbitrarily small, 100, 1,000, okay, a constant. So what we accomplish is basically a reduction of seedless extraction to seeded extraction. And the construction tolerates constant level noise. And there's some trade-off between the error and the number of devices. And the error can be made very close to optimal. So I understand I'm running out of time. So I'm going to summarize some implications, and I'll be done. So one application of our 2 papers is we can do unbounded expansion, and it's robust against noise. And let me jump to the next slide. So here, when we put these 2 papers together, here's a result we have. We can start with K bits of mean entropy. K can be some arbitrary small constant. Sorry, it can be a small constant. Then use the second extractor. We get some true randomness of K bits. And then using unbounded expansion protocol, we get arbitrarily long output. And it's all secure against the adversary. And the error is exponentially small in K, which is close to optimal. The optimal one, which is 2 to the minus K. And we can translate the Minushi protocol for generating randomness to do key distribution. In this case, we have a new result saying that Alice and Bob, they only need to start with a very short seed in order to produce a long shared key. And this is a trusted device and robust key distribution protocol. So a physical implication, or maybe a little bit philosophical, is that we have a very strong statement about randomness in our world. So true randomness in nature either does not exist, or it exists in almost perfect quality and unbounded quantity. So we are not stuck in the between world where we only have weak randomness. And we can use our result to mitigate a freedom of choice loophole in the build test by starting with weak randomness, getting almost perfect randomness, and then run a build test. I think I'm going to stop here because I'm running out of time. Right, am I?
Still about 7 minutes.
I do. Okay, good. Then at least I can talk about the open problems. Okay, so I want to talk about methods briefly. So the foundations of those protocols are build test. Okay, and so here's how I summarize the building blocks of those protocols. I call it a classical test of a quantum dot. If it sounds like a quantum dot, it works like a quantum dot, then it must be a quantum being. So the protocols will be classical tests on the devices and see if those devices behave like quantum devices. And the test will be will have those property that we call robust, or then in courses call them rigid. So if those devices behave, so this is the property, the rigidity property. If those devices behave very closely to ideal quantum devices, then they must be very close to the ideal quantum devices. So from the classical behavior, we can infer the inner working must be close to certain ideal quantum behavior. And ideal devices will be able to generate perfect randomness. And we know CHSH is one such test. And I'm going to skip that. So there's one challenge for applying CHSH game, for example, those games for randomness. So remember in playing CHSH game, we require that the input is uniform to the devices. And we may be consuming other randomness just to get one bit. So in playing a game, we need 2 bits of randomness. So in one, if you are outside the field, so there's this game that we need 2 bits as an input to the devices, and we get 1 bit out. So we're consuming more randomness than we get. So that's a problem. And in the case of seedless extraction, when we don't have true randomness, we don't have perfect randomness to start with, we have additional problem. The input to the players, to the quantum players, we cannot guarantee to be globally uniform. So our goal is to generate globally uniform bits. And to play the game, those building blocks require global uniform bits to start with. So it's a chicken-egg problem. Okay. So those challenges. So one solution to the first problem of consuming too much randomness is what I call mixing work and play. Okay. I have a 6-year-old, and I was very proud one day I make her do the dishes. At the same time, she felt very accomplishing playing. So in our setting, work is to generate randomness, but the input is fixed. The input to some non-local game is a fixed 0, 0. I put Einstein in between because I restrict these 2 devices from communicating in playing a game. So play is to run the non-local game with uniform input. Okay, so in playing, it consumes randomness, too much randomness. But in working, it does not consume randomness. So one idea is to mix these two things so that if each device, so that each device cannot tell if he is playing or working. Right? So when the input is 0, it could be working, it could be playing. So if the device is trying to cheat, trying to output some deterministic outcome, then there's a risk of it failing.
I think you need a third Einstein in there between the
Right.
If they could communicate, then you could tell.
I need a lot of Einstein. Here earlier, yeah. So here's protocol from QuaRC and Yaoyun, and it's an adaptation of an early protocol by Varsity and Vitic. So there we have two devices playing a lot of games, and we choose a small fraction of those games for testing, consuming a very small number of randomness. And then a lot of randomness for, and then the rest of the rounds will be generating rounds. Okay. And that's a protocol that intuitively you think must work, but proving it works turns out to be very difficult.
Can you define choosing?
Great, sure. So this in the context of seeded extraction, I have some uniform seed to start with. They're very short, right? So I'm going to make use of those coins, so that for each round, I toss a very biased coin, with probability P, I will choose that round as a testing round. And P is a very small number, so therefore I'm going to choose a small number of rounds. But they are chosen IID.
Then you don't put any assumptions on how good your whatever device, what you use, what you
Exactly, that's the whole point. I don't know what's going on in devices. So there are a lot of work to make it make the proof work. So there are multiple ideas involved, and we have to put together several pieces of puzzle to solve this problem. And I want to highlight one. Actually, I guess I'm running out of time already, right? Okay. So maybe I'll just go to the open problem because those are more exciting for you. You may be able to solve those problems. If I have to talk about one single problem, okay, there are many problems. One single problem is there a perfect physical extractor? So earlier I described this model of physical extractors. So there are multiple parameters. By perfect physical extractor, what I mean is every parameter is optimized simultaneously. Or as opposed to there are some inherent trade-off between them among all the parameters. So that's the major problem I hope to see somebody solve. I'm going to stop here. Okay, thank you. Yes, Joe.
Very nice talk, of course. You mentioned at the beginning we need 1 trillion bits a day.
At least.
At least.
According to the program.
Do you have a sense of the rate at which you can produce random?
That's an excellent question. Yeah.
Hold on.
Yeah, that's
Second
excellent.
part of that.
Yeah.
How fast can you produce?
Okay, good. So,
and what are the limits to producing as fast as you need?
okay, I think it's optimal. It's almost best possible in terms of the bit rate. So every basic operation, on average, one operation will produce 1 bit, a constant bit, constant number of bits. So in terms of bit rate, it's almost optimal. In the case of,
Can you give me a number? Can you give us a number?
I think there's a trade-off between the error parameter you hope to have and the output length. But it's almost optimal. But that is in the seeded case, assuming you have some short seed to start with. I think it's almost perfect, except for one problem that I don't know what is the least requirement on the source, like entanglement. A major problem is it possible to produce true randomness without entanglement? I conjecture it is, okay, but works need to be done. But in the seedless case, meaning that when the input is not perfect, there's a big room for improvement. So we have to use a lot of devices, a lot of Einstein, and which is not practical. And that's where I see big improvement can be done. Or maybe essentially, maybe there's a strong no bound saying that we can reduce the devices. That's also possible. Okay. And Giles.
So at the beginning, you defined true randomness in terms of the error approaching zero.
Yes.
So I have two opposite questions. If I put on a Microsoft hat, I would ask, what about particular values of parameters, how small do the errors get, and so on. If, on the other hand, I put on my mathematics hat, I ask, how fast is that asymptotic approach to zero expected to go?
Okay.
What would you want, for instance, in some of these open questions?
Sure. I guess these two opposite questions can be answered by me switching the two hats, and then there's a simple answer to my question. But more seriously, okay, so we have two scenarios, right? Seeded and seedless. Overall, I think seedless, there's a lot of room for improvement. But in the seeded case, the error actually scales very nicely. The error is negligible function of the upper length. It's very nice. And I haven't thought about the Microsoft question yet, but maybe that's why we need our industry to work on this as well. Okay, thank you.
Any other questions? Anyways, let's thank you again.
Thank you.
Okay, so now we're going to move on to our next talk. So our next speaker is Ben Reichardt, and Ben's going to speak to us about classical command of quantum systems. So let's welcome Ben.
Thank you. Yeah, so this is joint work with Wolfganger and with Umesh Vazirani. And the main question I'd like to ask is how we can characterize an experimental device. It's a very general physics question. Of course, you run tests on it or whatever. But the difference I want to say is that we want to characterize it with extremely high confidence. So imagining that you're completely paranoid and you don't trust anything about this device, and you're worried about loopholes or people cheating you, or you're really totally unsure, and you still want to be able to characterize the device and understand how this experiment works, or possibly even control it. And there's lots of problems here. One problem is that any device, any real experimental system is going to be quantum mechanical. And this means that if it's an interesting system, it's going to be exponentially complicated potentially, right? Because just a quantum state on n qubits requires potentially exponentially many n parameters to describe. And furthermore, we are essentially classical. So our interactions with this device, we only get classical information out. We can measure the system and we get some classical information out. We can measure it again in a different direction, whatever. So it seems like they have this extremely complicated quantum system, and we're only able to access it classically, and it doesn't give us a lot of hope to be able to solve this problem in general. And there's other problems as well. So this is sort of related to the previous talk. A trivial way of generating random bit is just to prepare the state uniform superposition between 0 and 1, and then measure it in the computational basis and the 0-1 basis. So you'll get 50-50, 0, 50-50, 1. And the problems, as we saw, like if there's some slight bias, you're not going to get 50-50, you're going to get 51-49. There's other problems, like maybe when you do this twice in a row, there's some correlation between the bits for some reason. The states are correlated. Or there could be completely crazy things going on. Like it could be that actually the device was manufactured by the government, and it has a random string inside in some tiny little corner of the device that you can't even find very, very, very easily. And it's not random at all. It's actually deterministic, just pretending to be random. And so we'd like to have the correct security model. And you might imagine that this is really too paranoid over here. We don't have to worry that much. But the problem is, I think, is that it's not so easy to figure out where you should draw the line if you're worried about security. Exactly what kinds of faults or errors in the devices you should worry about. You could write down a list, and you could just keep on adding and adding and adding to the list. So instead of that approach, I'm just going to start with the most paranoid assumption, security assumption possible, which is that actually the device was manufactured by the enemy, by your adversary, and it's trying to trick you. And yes, this is paranoid, but the advantage is that it allows us to deal with any kind of security model that's weaker. We don't have to specify it too carefully. And if you think about it for very long, so here's my device. The model is that I have no idea what it does, and it's made by the adversary. And if you think about it for very long, this is a completely impossible problem to try to understand what's going on inside this black box device when you can only access it by asking questions and getting answers. But the interesting thing is that actually if you have two of these black box devices and you've at least one Einstein, then it does become possible. So, and so this is really the model we're going to work with. I'm going to work with now. I'm going to say we have two black box devices that can't communicate with each other. Yeah.
Do we need to assume that the two black box devices are identical?
No.
No. Okay. Good.
I just copy pasted.
Two devices and not one.
Well, yeah, that's the problem, right? I mean, I guess you have to assume that they're. So I say we have Einstein, but in this protocol, we're actually going to require lots of interaction. So it's not going to be possible to ensure it just by separating them by a large distance. You're going to need lead boxes and stuff like that. Okay, so here's sort of what I'm going to start with, which is this CHSH game. And so here we have a referee. This is like me, the experimentalist, and we have two devices, Alice and Bob, two players. And the way the game works is you send them each a random bit, A and B. So it's using two random bits, as we saw, and they send back their answers X and Y. And to win the game, what they're trying to do is they're trying to get their answers X and Y. The XOR should equal the product of the questions. And if you think about it, if these devices are classical devices, there's no quantum mechanics, the best thing they can do is they can reply 0. If they each reply 0, the XOR is 0, which means that 3 out of the 4 times you're going to equal the product of A times B. The product of A times B will be 0, except if they're both 1. So that's the best you can do classically. You can win 3/4 of the time. Quantumly, it's a little more complicated, but here's the best strategy. They can share an EPR pair, so it's a 2-qubit entangled state, 0, 0, plus 1, 1. And they can make the measurements that I've sort of drawn here, depending on what questions are asked. And so then they just return the results of those measurements. And it turns out, if you look at this picture for a little bit, you can see that this strategy wins the game with probably about 85%. It's cosine squared pi over 8 is the exact number. And so there's a gap there. The quantumly, you can win the game with 85%. Classically, you can win the game only with 75% probability. And so this game has been used quite a lot by experimentalists to test quantum mechanics, or to test that you have a quantum mechanical device. So what you do is you run this test 1,000,000 times, and you just see how many games they won. Right? So if they win 800,000 of those games, then there's probably some quantum mechanics involved, right? Because classically, you only expect to win 750,000. It's very unlikely that you'll win 800,000. I mean, they could get lucky, but it's very unlikely. But I'm going to go much further than just testing that devices are quantum mechanical. As I said, I want to understand exactly what's going on inside these devices. I want to characterize these systems very well. And so a first step to talk about it is actually this strategy that wins with 85% probability. It's essentially unique. There's only one quantum strategy that wins with the cosine squared pi over 8 probability. It is this one. It has to use an EPR pair. So that's sort of interesting, I guess. It's sort of trivial. It's not that useful. We want to go a lot further. And so what I'm going to do is, here's our main theorem. We're going to try to come up with a way of testing that these two devices have many entangled many qubits worth of entanglement, not just this one EPR pair. We want to show that they have a very interesting, complicated quantum state.
Strategy gives you 85%. What if we lower the expectations to 80%?
Yeah, so that's why I say robustly unique. So if it's 85% minus epsilon, then you're sort of square root of epsilon close to the unique strategy in some nice metric. If it's so that's where epsilon is pretty small. I don't know if like 80% exactly. I don't know exactly how the constants are, but yeah. Actually, people have studied that though. So they do have graphs showing like 80%, 81%, what the fidelity you have to have with the EPR pair, I think. Right. Okay, so here's the theorem that we're gonna show is we're gonna consider playing many games one after the next. Okay, so in sequence, and so what this means is you send random bits A1, A2, B1, B2, and you get the answers x1, x2, y1, y2, and they just have to play each game and win each game separately. And here's the conclusion: if the devices win. So the omega star should be 85% or cosine squared pi over 8. If they win almost the optimal number of the games with high probability, so if they have a strategy that allows them to win almost the optimal fraction of games, then it must be that at the beginning of a randomly chosen subsequence of games, the strategy for that subsequence of games has to be essentially ideal. Meaning that, so here what I've done is I'm playing capital N times little n games, one after the next. And so you think of it as just capital N's, let's see, each of these is a block of a subsequence of games. And what I'm saying is the conclusion is that if you choose one of these random blocks, then in that block of little n games, they have to be using the ideal strategy, which is to say they have little n EPR pairs in tensor product. In the first game, they measure the first EPR pair. In the second game, they measure the second EPR pair. In the third game, they measure the third EPR pair, and so on. So it's actually a very simple strategy that they have to be using. You could imagine them doing almost anything, right? They could have an arbitrary entangled state to start with. They could apply arbitrary measurements. The rules that they use to play the games could be completely arbitrary. The rule you use to play this game could depend on what happened in the previous game or the previous game or the previous game. But this theorem says that that doesn't happen. You play every game independently. And this is actually a very nice theorem because it actually does establish that these devices have quite a lot of entanglement. They have to, if they pass this test, then they have to have at least little n bits of entanglement. And so this is what we want to show. And unfortunately, it's actually quite inefficient. So the parameters we have is capital N is polynomial of little n, it has to be. Where the exponent of the polynomial is probably, I don't know, I don't want to say, it's probably like 50 or 1,000 or something. And also the error is pretty bad. So if you're winning with probably 85% minus epsilon, the error here in this approximate is actually growing like again some crazy polynomial in epsilon. Yeah.
I missed something. The little n seems completely arbitrary to me. Why did they need little n EPR pairs? Don't they need little n times big N EPR pairs to play?
Intuitively, yes, but I don't know how to prove that. So little n is completely.
Once they used up the n in the first set of little n games in the block, where did they get the next n EPR pairs from?
Well, so if the devices are honest, then they'll have to start with capital N times little n EPR pairs. Yeah. Okay. If they're dishonest, I'm proving that they have to have at least a little n.
Okay.
Yeah. So one interesting open question, which I think is quite interesting in this area, I don't know exactly what the applications of this are, but it's sort of a very fundamental question in quantum information, which is exactly what the right kind of error is and how it scales. And in particular, it would be interesting if we could understand how to run these kinds of tests if the noise rate were constant, which I guess is more physically relevant. And so, for example, one conjecture you can make is that if you play little n CHSH games and they win 84% of those games with high probability, which is something that you could actually imagine implementing in a real-world system, then I might conjecture that they have to share roughly little n EPR pairs without this crazy polynomial loss. I have no idea how to prove this, but I think it's a very interesting question. Okay, so I've said the theorem. I haven't really motivated this theorem. The idea is just you have these devices. You're trying to prove that trying to establish that they must have some interesting quantum state underneath them. So lots of entanglement. But why do we want to? Why is this actual form of the theorem useful? And so let me give one application. There's actually a few of them. So one application is what's called delegated computation. So in delegated computation, you have like a cell phone, and it has to run a computation that's too expensive for it, so it wants to outsource it to an untrusted server, for example. And so you don't trust the server, so you want to make sure that the result it gives you is correct, and also maybe you don't want to even tell it what you're trying to compute in the first place. So classically, there's a lot of results. Quantumly, there's what's known before. It was known as semi-quantum delegation. So in this kind of result, you start with some quantum circuit you're trying to apply. So for some reason, your cell phone wants to apply a quantum circuit, and you're outsourcing it to a quantum server. But you can't be fully classical. You need to be able to prepare 1-qubit quantum states and send them to the server, unknown, sort of random 1-qubit quantum states, and send them to the server. And then the server does a bunch of processing on these states and sends you classical messages, and you have to send other classical messages. And that gives you your delegated quantum circuit. Actually, what we're able to do is come up with fully delegated quantum computation. So your cell phone, the weak guy, can be fully classical, and you can delegate a quantum circuit to untrusted quantum servers. But now we need 2 quantum servers, and we need an Einstein between them. And sort of intuitively, if you're trying to come up with a scheme like this, you might start with this scheme here, and try to translate it into this picture. So you could have the classical verifier and Alice together preparing these 1-qubit quantum states somehow, and then teleporting them over to Bob, and then having Bob act as a quantum server in that picture. That's sort of a first approach. I don't know how to prove how that works, but I guess it's sort of an intuition for how you might approach this kind of problem.
What if you have one server, but instead of sending prepared quantum states, you send perfect random bits? Can perfect random bits serve instead, play the same role?
Well, if the server is exponentially powerful, then yes. It's unknown if the server is polynomial time quantum circuit or quantum device. I don't know. Yeah, we don't know. That's a good question, though. Okay, and sort of the problem with all these kinds of schemes is that it just seems like it's completely impossible to analyze them rigorously. Because these devices could be doing completely arbitrary things when you send them these classical messages. you tell them to apply a gate, and you tell them maybe apply this 2-qubit gate because that's what you want them to do next, and they apply an arbitrary unitary on this infinite dimensional quantum state. And you have no idea what they've just done. You don't know what their Hilbert spaces are. Again, it's infinite dimensional. You don't know what their state is. It seems like it's really hard to understand what's going on when you try to give a security analysis of any of these kinds of schemes. But the trick is this theorem for playing multiple sequential CHSH games actually starts to give us a structure on their internal quantum state. They have to be using EPR pairs, and they have to be measuring them one at a time in a very nice way. And that's sort of like our foothold, which lets us to bootstrap up to get complete control over anything that these servers do. I think actually the interesting thing here is I started with this idea that controlling quantum systems is extremely difficult. Because they're quantum, they're exponentially complicated, we're classical, we can only measure them, and so on. But actually, our results turns out to be much stronger than anything that's possible classically. So if you try to understand a classical device and give it tests and get answers, well, you can verify that it's giving you the right answers and so on, sure. But there's no way of knowing exactly what's going on under the hood. If you can't open the box. It could be doing completely arbitrary things under the hood and just giving you the right answers in some weird way. Quantumly, it turns out that the only way of passing these CHSH tests is if they share EPR pairs and if they're doing these particular measurements. And the only way of, we'll have more tests in a second. The only way of passing these more general tests is if they behave in these very particular ways. So actually, without looking under the hood, we know exactly what's going on in the states of these systems. So we're getting much stronger control quantumly than is even possible classically, which is sort of interesting. Right. Okay, so here I'll give you. I have a bunch of other slides on this, but here's like the one slide that's probably way too short that sort of explains how we can bootstrap security based on just the sequential CHSH games. So what we're going to do is we're going to run one of 4 protocols at random. So a quarter of the time, or actually like 99% of the time, I think, we'll just play CHSH games with these 2 devices, one after the next, and this is what they should be doing if they play honestly. They should be applying these measurements. Okay, and you check that they win 85% of the games, 84% of the games. Okay, but then a quarter of the time what you do is you'll run a different protocol. So with Bob, with Alice, you'll keep on playing the CHSH games. So you'll send her random bits, 0s and 1s, and she'll have no idea. That device will have no idea that you're not in this picture playing CHSH games. But with Bob, you won't ask him to play CHSH games at all. You'll instead ask him to make some interesting measurements. In particular, you'll ask him to prepare certain states on his halves of the shared EPR pairs. And the point is, Bob now can cheat arbitrarily. You have no idea what Bob's really going to do, but you know that Alice is still playing the CHSH games. And so you can use her measurement results for those games to tomographically verify that Bob does what he's supposed to be doing. And similarly, in the third protocol, we're going to have Bob playing the CHSH games, and Alice, we're going to ask Alice to do some interesting measurements on her halves of the states. And again, so Bob's results will sort of give us a tomographic test of that Alice is behaving honestly. Yeah?
Just a question about terminology. Do you think control is exactly the right terminology for this, given that Alice and Bob could just arbitrarily decide not to play the game and jam the protocol?
Right. I don't know. So I think, actually, what did I call it? Control? Here I call it command. But I don't know. Yeah, right. The devices can always just decide not to cooperate, and there's nothing you can do. Yeah. So there's always an assumption that if the devices pass these tests, then they must. Yeah.
This resembles prisoner's dilemma situation.
I hope not. Why? Well, no, I don't think so. I mean, the devices should always be trying to defect in our analysis. We're assuming that they're trying to be dishonest, both of them. And they just can't. Sorry, so there's our protocol. So the first protocol is just the games. Then we have one protocol where Alice checks Bob, one protocol where Bob checks Alice. And then finally, in the last protocol, we just plug together this part where Alice is doing interesting things and Bob is checking, and this part where Bob is doing interesting things and Alice is checking. So now we put this and this together. So Alice and Bob are both doing interesting things, but they have no idea that the other person isn't checking them. So they have to keep on playing just as they were in these two protocols. And finally, now they're both doing interesting things. They have an interesting state. They have these EPR pairs. That's a pretty interesting state, so they can do really interesting computations. You can do an arbitrary quantum circuit. By teleportation is a trick. So this crazy picture here actually implements this very simple circuit here. Sorry, you might be able to see that. It'll take like 10 minutes.
Quick question. So from Bob's perspective, the information sets are such that Bob cannot distinguish between A and C. But he can distinguish whether he's either an A or C or B and
T. That's right.
Whereas Alice, it's A and B are indistinguishable,
Yeah.
and C and D are indistinguishable.
That's right. Yeah. But they're all sort of tied to each other. Exactly. Yeah.
So that you can not only force them to do the computation, but they won't, neither of them knows what computation they are running.
Yeah, that's actually very easy. I mean, up to sort of like they're going to know like the size of the computation unless you try to, blind it somehow, like buffer it or something. But yeah, it's essentially so in computation by teleportation, you just need to ask one of the players to prepare these resource states like Hadamard gates and CNOT gates and whatnot, and the other player sort of links them up, but they have no idea how they're being linked up. So they know how many gates the circuit has, but they have no idea how they're wired up at all. Oh, that's what you mean.
Well, I sort of was asking so.
Yeah, I don't know how you could stop that, right? Because after the fact, they know as much as you know. Yeah. All right, so that's sort of how this starts to be useful. So maybe, how long do I have?
We have about 30 more minutes, or 20 more minutes.
Oh, okay. That's good. So maybe unless there are more questions about this, instead I'll go back to the theorem and start to explain sort of the difficulties in understanding a theorem and proving a theorem for just the CHSH games. Let's see. Right, so the proof actually has 3 steps. The first step is just basic classical statistics. So you say, if these devices win 85% of the games with high probability, what that means is that if you look at a random block of polynomially many games, then it must be that every single one of those games you have to have played that game with 85% winning probability. It's just sort of like a sampling thing. And this is sort of necessary. I mean, for example, these 2 devices, Alice and Bob, they could decide that they could decide in advance that they're always going to cheat in game number 5. And statistics, they're always going to return 0 in game number 5. And there's nothing you can do about that. You can't force them to use an EPR pair in game number 5. You can just say that sort of statistically you can avoid that by saying if I look at a random game, or a random block of games, you're missing game number 5, and in that block they have to be playing pretty well. Okay, so now there's 3 steps. All right, so the first step says that in every game that they play, they have an EPR pair that they're using, or a state that's close to an EPR pair that they're using. And so there's a qubit on Alice's side and a qubit on Bob's side, sitting inside their Hilbert spaces. So this is just a picture. This is supposed to be Alice's Hilbert space. It's some infinite dimensional space. And these balls are each supposed to be a qubit. And they sort of overlap because we don't know how the qubits relate to each other at all. And furthermore, there's lots of qubits. So the game 1 qubit is here. In game 2, you have maybe 2 or 4 qubits, depending on the outcome of game 1. And in game 3, Alice could use any of, I guess, 4 qubits, but I think it's actually 16, depending on the outcome of the first 2 games, and so on. So that's the first step of the proof, is establishing that they are using qubits hidden inside their Hilbert spaces, but we have no idea how these qubits relate to each other, and there's tons of them. The second and most interesting step is to start to show a tensor product structure. So here, I showed that the qubit that Alice uses in game 2 is in tensor product with the qubit that she uses in game 1. So it's sort of like independent of what happens in game 1. And so in the picture, they're not overlapping anymore. But again, potentially she uses different qubits in different games depending on what happened in the previous games. And finally, in a sort of a technical step, we showed that actually there's no history dependence. So the qubit they use in game 2 does not depend on what happened in game 1. Game 3 does not depend on game 2 or game 1. But the most interesting step is actually showing that these qubits don't overlap each other, that they're in tensor product. And I should just say that this kind of picture where qubits are balls and overlapping means they're not in tensor product, this is completely misleading, and you should not think too closely about what this picture means. I mean, if you have an infinite dimensional Hilbert space, a qubit is not a ball. A qubit is really, what is it? You have to choose a basis and say that this is my qubit. So I guess it's like a hyperplane, which is like the poly X measurement, and another hyperplane, which is a poly Z measurement, and they should be at like dihedral angles of 45 degrees between these planes everywhere. So they're not like balls at all. And if you have 2 qubits, they don't overlap. You just have these hyperplanes sitting around in different directions. But it's still nice to think about sometimes. Right. So it's hard to appreciate how many things can go wrong with this kind of theorem. Pretty much anything you can imagine. So like, first of all, we don't know that they're playing using EPR pairs. There's no way of establishing that these devices use exact EPR pairs, because all we have to test them is statistics. So we can only say that they're using close to EPR pairs. And this is always a problem, because if they're using close to EPR pairs, then the errors can be sort of arbitrary, and they can overlap each other in small ways, and then the errors can start to blow up very quickly. So here's kind of a picture. I have games 1 through 7 that each have slightly overlapping qubits, and the problem you're worried about is that game 8 uses a qubit that completely overlaps game 1, because somehow the errors have accumulated in those 7 intermediate games that now they're not in tensor product or even close to being in tensor product anymore. So it's fairly easy to show that if you just have 2 games one after the next, they have to be almost in tensor product. But the question is how far you can push that kind of statement. So here's one way that errors accumulates. So I've drawn 4 qubits. I'm going to use 5. Let's see. Yeah. So I'm going to play 5 CHSH games using 5 EPR pairs. So 1, 2, 3, 4, 5. But actually in game 1, I'm not going to use this first EPR pair. I'm going to use most of this EPR pair and a small fraction of the last EPR pair. In game 2, I'm going to use most of the second one and a small fraction of the last one. In game 3, I'm going to use, and so on. And so by the time I get to game 4, I've accumulated enough error over here that maybe moved this qubit all the way into like some other position, like back into this position. Because that's just how the errors, that's the direction that the errors were going. And so in game 5, I measure this qubit again. A second time, I measure the same qubit. And because the EPR pair has moved into that position. So this is kind of a non-tensor product strategy. It's not the ideal strategy. So it would be a counterexample to our theorem if this were allowed. And you could say, how can this happen? Well, first of all, the errors are adding up, and there's polynomially many games in our actual system, not 5. But it's even worse than that, because every time you make a measurement, any error gets renormalized when you measure a quantum state. So you take your state psi, you measure it, you get pi psi, then some renormalization factor. if there was an error, then the error is also blown up. And so this is another problem. And there's lots of other reasons why errors accumulate. This is just a first example. So let me sort of give you, I don't think I'll go into any detail really, but let me just give you a very high level intuition for why this might work, and how the proof works. And actually, the idea is that Alice's Hilbert space, we know nothing about Alice's Hilbert space. Bob's Hilbert space, we know nothing about that. But the one thing we do know is that Alice and Bob are in tensor product with each other. And that is sort of the key thing. So we're going to use the tensor product structure between Alice and Bob to construct a tensor product structure, substructure within Alice's Hilbert space and within Bob's Hilbert space. And so the trick is, we have two tricks that we're going to use. So the first one is, and these are both easy to verify. So the first one is just if you take an EPR pair and you act on the first half, that can just as well be done on the second half. So this is an identity. If M is any 2 by 2 matrix, that's the identity 2 by 2 matrix. And you multiply this out, this is true. You get M transpose on the right. So an operation on Alice's side is the same as an operation on Bob's side, the transpose. The second fact is that quantum mechanics is local. So anything Alice does actually can't affect what Bob has in expectation. Right? So if you don't condition on Alice's measurement result, then Bob has no idea what Alice is doing. You can't. All right, so how are we going to use this? Let's see. So we're playing n games. And let me just try to show that game n is sort of independent of game 1. And game n is in tensor product with game 1. So first of all, they play the first game and they collapse this first EPR pair. So now this is like a measured qubit. And then they play games 2 through n minus. Come on. 2 through n minus 1, and then they play game n. And we're worried about a situation where game n is somehow wrapped around and is using the same qubit again. Okay. So what we're going to do is we're going to use fact 1 to pull these games, to pull Alice's operations in games 2 through n minus 1 over to Bob's side. What that means is, by fact 2, this qubit here cannot be affected by games 2 through n minus 1. Because anything done on Bob's side can't affect Alice's state. So it can't affect this qubit. And so what that means is that after n minus 1 games, this qubit is still collapsed. It's still whatever it was after the first game, like ket 0 or ket plus or something. And so therefore, when we play game n, this qubit is just like ket 0 or something. It's completely useless in the CHSH game. It's not an entangled qubit or something. And so therefore, game n has to be using a fresh qubit in some other direction. That's the idea. And so that shows that game n has to be in tensor product. The qubit used in game n has to be used in tensor product with the qubit in game 1, even though a bunch of stuff happened in the middle and lots of errors accumulated. That's sort of the idea of how the whole proof works. Obviously, you have to be more careful because we're trying to show that everything's in tensor product, not just n with 1. But this is sort of the biggest idea. Let's see. Right, so I have a few slides here which sort of show explicitly they construct the tensor product structure within Alice's Hilbert space and show how that's done. I don't know where that came from. But I don't know if that's, oh, sorry. But I don't know if that's so interesting unless there's questions about that. It's interesting to me. Maybe let me just instead finish up or ask if there are any questions.
Maybe I'll just answer a question.
Yeah.
So I'm trying to see if I can come up with a different way of showing your result. Suppose at some point I can argue that for the little n
sequential gains. I know that everyone condition on the previous outcomes is some tiny epsilon away from IBM. And can I just say that overall they are n times epsilon away from the tensor product?
No,
Yeah.
I don't think so.
Okay. Because the tensor product, you enable to actually sequential tensor products.
No, I mean, I just, it's yeah, because there's no reason errors should just add up. Errors can blow up much faster than that.
So if it doesn't add up linearly, is there any other about how the error can?
Like, I think trivially, like, let's see, yes, there is something you can say, but it might be like double exponential or something like that. Yeah. I mean, because, well, there's one exponential just from renormalization, and there's another exponential as well. At least another exponential, which I guess probably comes from this second point, which I erased.
Okay.
But yeah.
So that bigger long series function, is it constructed meaning that it's suddenly, but it could be out of bound, but have you thought about some explicit tuning strategy that will satisfy that conditional probability?
Yeah, I think this is a very interesting open question as well, because it's coming up with counterexamples to these kind of theorems is very hard, right? Because you have to come up with some very interesting quantum state that's highly entangled, and it's not a tensor product state, but it lets you sort of cheat in some interesting way. I don't know how to do this. I wish I had better ways of coming up with counterexamples. That would be just as interesting as a theorem.
So that means still possible that error might end up meaningful, but that will call strong results.
Yeah.
Other questions? Herman? If not, let's thank Ben.
Thanks.